Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to solve steal packages. This prompt states, write a function that returns the maximum amount you can earn without robbing two houses in a row. The input to the question is an array of integers, and we need to calculate the maximum value we can earn by stealing packages from any of the houses, with the only constraint being that we can't steal from two houses in a row. These houses will sound an alarm if we try to steal from consecutive houses, so there must be at least one space between houses when we try to steal the items. So the array we're given matches the value of the packages at the house. So with the first example, we have houses with values 2, 3, 5, and 1, as we see from the array. And then the second example has 5 houses with the values 1, 10, 3, 2, and 5. The answer to the first example is 7, where we steal from the first house and the third house, and their sum of values is 7. And then the solution to the second example is 15, where we steal from the second house and the fifth house. So notice that we don't have to steal from every other house. Here we skipped 2 houses and stole from the second and the fifth. The only constraint that we have to follow is that we can't steal from houses next to each other, but there's no constraint on how many we can skip to get the largest answer. Let's start with some simple examples and build up intuition. If we have an empty array, that means there are no houses, so we simply return 0. If we have one item, then there's no choice to make. We just return that item as the answer. And one thing we should note is that these values will always be positive. A negative value doesn't make sense because that would mean we're leaving money there, which we would never do. Also, we can assume that if a house is listed, it has a package. So this means it will never be 0. So these package values will always be positive numbers in the array. Now let's consider a case with 2 houses. For each, we'll just steal the largest item. We can't steal from 2 in a row, so we just have to pick whichever is larger. In the first case, it's 10, and in the second case, it's 20. With an input containing 3 items, we now actually have a decision to make. We can either steal the first and the third item, or the middle item. We can't steal the first and the middle, or the middle and the last, because then we would be stealing from consecutive houses. So here we would try summing the first and the third, and then compare that to the middle's value. Whichever is larger, we would either steal the first and the third, or the middle. And notice, if you steal the first, you're always going to steal the third. As we noted, these are always going to be positive values, so if you steal one and skip a space, you're always going to steal one at least 2 spaces away. So for example, if we swapped this 20 and 5, well, we know 20 would be larger than the 10, so we would immediately steal that, and then since there's a space between the 20 and the 5, we would also steal the 5 regardless. And now, let's consider an input of 4 items. We're now starting to get more combinations and interesting patterns. For example, with 4 items, we can steal the first item and the last item, and that means we skip the 2 middle ones because they're touching the first and the last. Or we can steal the first and the third, or the second and the fourth, because then we're leaving one item between 2 houses. But still, in this simple case, we can do some simple addition to find the answer. And then with 5, the possibilities grow even larger. But in this case, we'll start to recognize some patterns forming. And instead of looking at numbers with the houses, let's just consider the houses we would or could steal from based on the constraints. The first possibility is stealing from the first, third, and last house. Notice that if you steal from the first and the last, you couldn't steal from the second and the fourth, but then you would always steal from the third or the middle item because we know it's positive and it wouldn't be touching either of the ones we've stolen. Then another case is where we steal an item and then leave 2 spaces and steal one from 2 houses apart. So that's either the first and the fourth or the second and the fifth. And then finally, you could steal from the second and the fourth. So this is getting a bit abstract, but the reason I'm looking at the patterns first is to show that we have isolated cases that we can solve. We don't have to solve the entire array to get the solution. We can actually see we have subproblems. And if we solve these subproblems, we can combine their answers to get the overall solution to the question. So really, this whole problem boils down to the 3-house example. If we solve this problem at each point, we can calculate the overall solution. What we do is start by iterating from the beginning, and then as you get to each new house, you can either steal the current house or the house behind it. So in the first case, when we get to the third house, we can either steal the third house and the first house, or we recognize that the house behind it, the adjacent house that's touching it, is actually larger. So we can steal the item from that house and add it to the profit. So we're going to track the profit as we iterate through the array, and regardless of how large the input is, this strategy will work. So as we track the profit as we iterate forward, it's all about deciding if we should steal the current house and add it to the profit, which is the profit that was calculated 2 houses back, or use the profit from the previous house since we can't steal from houses that are adjacent to each other. And we're just repeating this decision at every point regardless of how large the array is. It boils down to the 3-house problem. So the key to this question is tracking the max profit. So for each subproblem, we're going to solve for the max profit at each point. So when we get to any house, we have a decision. Do I steal the current item and add its value to the max profit from 2 houses back, or do I use the max profit from the previous house? And this boils down to the 3-house example. The subproblem we're solving is finding the max profit at each item, so max profit of the I, for all the items from 0 up to the final item. We find it by taking the maximum between the value at a given spot and then the max profit from 2 houses back. So you're not looking at the value from 2 houses back, you're looking backwards through the memoization array for the max profit that you calculated at this point. So if we're at item 6, to solve this subproblem or find the optimal solution at this point, we look back at item 4 and find the max profit that we found at this point, and then we add this to the value at 6, and we compare this to the max profit from 5, and whichever is larger, this one plus this value, or the max profit from 1 house back, becomes the solution to this subproblem. And at each point before that and after it, we were doing the same thing. At house 5, we added the value to the max profit from house 3, and then compared that to the max profit from house 4. So what I want to make sure is clear is that we're tracking the max profit and then adding the value from a house. And then, as we continue to solve this subproblem and build up the solution by finding the max profit at each point, once we get to the end, when we find the max profit at this point, this is also the overall solution, because we built up the max profit as we've gone along by making the optimal choice at each point, and then using these values at each next subproblem until we reach the end of the input. And once we solve this, we'll have the overall global solution and can return that as the answer to this question. So we can use dynamic programming to track the profit as we iterate through the array. Then we just store the profit at each point by either keeping the current house and adding it to the profit or stealing from the previous house. So that means we either carry the previous house's profit forward, or we add the current house's value to the profit from 2 houses back. And we're making this decision at each point. So let's walk through this example and build it up step by step. We start at the first house and we have nothing to compare to, so we initialize the first spot to the first house's item value. Then we do the same for the second house. Then we reach house 3, and we can either add it to the profit from 2 houses ago, which is 3, so this house, 12, plus the profit from 2 houses ago, which is just 3, or we can use the profit from 1 house back, and that's how we determine the max profit that can be achieved at this current house. We know 12 plus 3 is 15 and larger than 11, so we store that in the array. And to solve this dynamic programming problem, this data structure that we're building is simply an array where each index corresponds to the max profit that can be stored at each house. So we saw 3 is the max profit at the first house, 11 is the max profit at the second house, and then 15, or 12 plus 3, is the max profit at the third house. And this was that 3-house decision. But now we continue on. We get to the fourth item, and we take 2 plus the max profit at 2 houses back, or 15. 15 is larger than 2 plus 11, which is 13, so we just carry forward the 15 to the max profit at this location. Then we move forward to the next item. The item at the current house is valued at 5, and the max profit at 2 houses back is 15, which we saw was 12 plus 3. So the max value at this point is what we add to the current house. So 5 plus 15 is 20. We either take this value or the max profit from the previous house. 20 is larger than 15, so that's the max profit at the current house. Then finally, we reach the last house. The value of the item at the current house is 20. Then we look at the profit 2 houses back, which is 15. So 20 plus 15 is 35, or we check the max profit from the previous item, which is 20. 35 is larger than 20, so the max profit at this point is 35. And now we've iterated through the entire input. Then we built up our dynamic programming array to store the max profit at each point. Then once we're done, we have the max profit at the final item, which is the overall max profit. So this is the solution. So what we're doing is classic dynamic programming. We're taking a bottom-up approach where we start at the beginning and then use this data structure to build up the solution we want by solving subproblems at each point. Then when we reach the end and have solved all the subproblems and continue to build up this max profit, or growing it each time as we move forward, when we reach the last item, we've calculated the overall profit and the solution by building it up and by combining the answers to the subproblems that we calculated along the way. So one case that I want to make sure is clear is when we skip 2 houses to steal items to get the max profit. So here the max profit is stealing the first item, skipping 2, and then stealing the last item. So we know this question boils down to the 3-house example, where you decide if you should steal the current house's item and add that value to the max profit from 2 houses back, or use the max profit from 1 house back. So we're building up the max profit as we go through each step, and the logic we use is going to handle the case where you skip 2 houses to steal items. We actually saw it in the last one, where we added 20 plus 12 plus 3. We skipped these 2 houses. And the reason is because we carry the max profit forward. When we're checking the max profit from the previous 2 houses or the current house, since 11 is larger than 10, it's also the max profit here, which is what we add to 50 when we check 2 houses back. We're solving the same subproblem as we iterate through. So when we solved it here, the answer was 11 because it was the max profit from the previous house. And then when we got to the last item, we checked 2 houses back, and the profit at this point was 11 because it corresponded to the house before and not the current house. So that's how we knew to add 50 to 11. So as we said, this is an array where we're tracking the max profit through the entire input. We know the possible max profit at each point. However, we don't actually need the entire array. When we're calculating the max profit at each point, we only care about the max profit from 2 houses back and the previous house, and then we decide if we should add the current house to it. So looking back at this longer example, we didn't need all these prior values once we got to the end. We only needed the current house's value, the 20, which was the max profit from the previous house, and the 15, which was the max profit from 2 houses back. And this allowed us to calculate the solution. So we don't actually need this array. We don't need to incur this O of n space. We only need 3 variables. One to track the profit from 2 houses back, one to track the profit from 1 house back, and then one temporary variable to move these items forward as we iterate. Then by tracking these items and variables, we can actually solve this in O of 1 constant space. So just to make sure that's clear, we don't need the array. We don't need to incur that O of n linear space to solve this with dynamic programming. We don't actually need the entire history of max profits. We only need the max profit from 2 houses back and 1 house back, and then we can make the decision at the current house. So now let's solve an example where we use variables instead of the array for dynamic programming. We have 5 houses with items valued at 1, 5, 10, 20, and 30. We initialize the max profit to 0, and the max profit from 2 houses back also to 0. Then we begin iterating through the input. The value of the item at the first house is 1. We set a previous max profit temporary variable to 0. Then we add the current house's item value to the max profit from 2 houses back. This is 1, and we compare that to the previous max profit, which we initialize to 0. We store the greater of the two, or the maximum between 0 and 1 plus 0, into the max profit. 1 plus 0 is 1, which is greater than 0, so that becomes the new max profit. Then we iterate forward. We store the current max profit in the temporary max profit previous variable. Then we compare the current max profit to the house's value, 5, plus the max profit from 2 houses back, which was still 0. This is 5, which is greater than the current max profit, so this becomes the max profit. Then to continue iterating forward, we set the previous max profit, which was the max profit before we got to this house, to the max profit from 2 houses back. This allows us to continue iterating forward. We move to the third house. We set the previous max profit temporary variable to 5, which is the current max profit. Then we add the house's value 10 to the max profit from 2 houses back, which is 1, so 10 plus 1 is 11. We compare that to the current max profit, which is 5. 11 is larger, so that becomes the new max profit. Then we store the temporary variable previous max profit to the profit from 2 houses back. We iterate forward. We set the temporary variable. Then we sum the current house's item value of 20 plus the max profit from 2 houses back, which is 5. So 25 is larger than 11. So that becomes the new max profit. Then we update the max profit from 2 houses back. And then we reach the final item. We set the temporary variable. And now we sum the current house's item value, 30, with the max profit from 2 houses back, which is 11. This is 41, which is larger than 25. We update the max profit. And then, since we're at the last house, this is the solution. So the max profit is 41, and we got these values from the first house, the third house, and the last house. But we use dynamic programming to calculate this by solving subproblems. At each house, we just sum the current house's value to the max profit from 2 houses back, which is something we continue to build up as we iterate through, and then we would take the greater of the max profit from 2 houses back plus the current item and compare that to the current max profit, which was calculated from 1 house back. Then we stored the larger of the two and move forward. Then once we reached the end, we were done building this value up and returned the last max profit that we calculated. And now let's just summarize the steps to the solution. We're going to solve this using dynamic programming, taking a bottom-up approach, but we realized we don't need a data structure because we only ever look at the max profit from 2 houses back and 1 house back. So we start by initializing these 2 variables. The max profit is going to be the max profit that we build up as we solve each subproblem. So as you solve a subproblem, it gets stored in this max profit variable. And then we keep an alternate profit. So this refers to the profit from 2 houses back. So then, when you make the decision at each point, you can add the current value to the alternate profit or use the previous max profit, which is the max profit from 1 house back. Initially, these variables will be 0. And then we just start to iterate through each house so we can make the optimal choice at each point. Since we're using variables instead of a data structure, we need to create a temporary variable each loop so we can move the values forward. Then it's time to make the decision. At each point, we can take the current house's value and add that to the max profit from 2 houses back, or just use the max profit from the prior house, which is the current optimal answer from calculating the solution to subproblems. So as we see, it just boils down to that 3-house question, and we're tracking the max profit. So at each point, do we use the current house's value with the max profit from 2 houses back, or do we use the max profit from 1 house back, which is the most recent optimal answer? Then whichever is larger, we store this solution to the max profit variable, and then we can move forward. So if we continue to solve this same subproblem for each step, or make the optimal choice by deciding if we steal the current item or not, once we solve this final subproblem and set the max profit here, this will also be the max profit overall, and will be the solution to the problem. The big O complexity for this question is O of n linear time and O of 1 constant space. We iterate through all n items, and we don't add any new additional data structures. And now we're ready to write the solution function steal packages. We initialize the max profit at 2 houses before, and the current max profit to 0. These are the variables we're going to use to track the max profit as we build it up while we iterate through the array. We iterate through all the items and grab each one from the package values. We create the temporary variable, max before current, where we store the max profit before we got to this house. Now that we've stored the max profit, we want to calculate the new max profit at the current house. So we take the max at 2 houses before and add the current item's value to it. Then we take the maximum of those values or the current max profit. So we've either determined we can create a new max profit or just roll the old max profit forward. Then, since we're iterating forward, we set the max at 2 houses before to the max before current, since this is going to be the new value at the next house. Then finally, once we've iterated through all the items, we've built up this max profit, and when we're done, the max profit from the last house should be the overall max profit because we continue to solve this same subproblem. So we return the max profit variable. Quick syntax fix. We run the code and the tests pass. So this question and variants of it are classic dynamic programming problems. The things you learned here and how you build up this solution by starting with the bottom-up approach and continuing to calculate your max as you iterate through is intuition you can use in many dynamic programming problems or even this specific problem itself. Thanks everyone, and I'll see you in the next lesson.